All right, good morning, everybody. So welcome back to Pre-Calc, and we're going to talk about logarithms today. All right. Oops. So I'll repeat myself a little bit from the first time we went over this, but not almost everything, okay? So just to kind of go over this a little bit again today. Right, that's logarithm. This is, again, it's about 16th century technology. That's when they came up with this stuff. At least in the form we have it today. Okay, there may have been earlier things, but they didn't quite think about it the same way we do. And the idea here is this answer here, this is an exponent. So if anybody ever asks you what a logarithm is, you can give them this very snotty answer of it's an exponent. Because when you take the log of a number, you get the exponent you were to raise this base to in order to get to that value. So the answer to any of your logarithm evaluations, you punch in log of anything into a calculator, that's the exponent. You're going to say 10 raised to that power is equal to this argument, okay? So if you're ever wondering, like, I can never remember where these pieces go, just try to remember, like, so if somebody who doesn't know what a logarithm is and you don't want to talk to them, you can just tell them it's an exponent and go along your way. So that's your answer, is your exponent. Okay, this is your argument. And then this one here is your base. All right. So the important thing to deal with, especially when you're dealing with logarithms that aren't like the easy ones, is that you have, this is how it works. Okay, that we have the base raised to the answer is equal to that argument. Okay, so my equivalent exponential form here, right, is the base raised to the y is equal to that x. All right. So if we go do an easy one, right, we're doing 10 or log base 10 of 100, right, equals what? And this is equivalent to 10 raised to what power is equal to 100. All right. So this one, I picked this one on purpose because for log base 10, all we're doing is counting the zeros, right? And it's going to be 2. 10 squared is equal to 100. So this question mark here, that is 2. All right. So sometimes they're not so easy. Okay, generally your book does do them so that they're pretty easy on this part. And I don't think I ask too many questions about log bases that aren't the ones you see almost all the time. But, what if we did log base 6, right, of 216 equals what? So 6 raised to what power is equal to 216? Okay. And I'm just going to go out on a limb, although I've been proven wrong. I've had a lot of students tell me that I think about this way too seriously. That any decent Dungeons and Dragons player will know that 6 cubed is equal to 216. So this should be a 3. I've had several of my students playing D&D that said, nope, that's not going to work. All right, I'm going to pause this for a second. All right, there we go. Okay, so yeah, let's look at the graph. Okay, so here on the side here, we've got a log base 5 of x, and they would like us to graph this thing and point out some features. Okay, so with the way we usually think about this stuff, right? The logarithm is the inverse function of the exponential. Okay, so log is the inverse of the exponential. So just like squares and square roots are related, logs and exponents are related. They have the same relationship. All right, and squares and square roots, we don't really have too much of a problem going backwards and forth, but you might have a bit of a problem going backwards and forth with logarithms. So one of the things about f and f inverse, right, was we had a domain for f and a range. Now, let me make a little bit more room here. And remember, they had this relationship, right? Actually, I'm going to go with a D and an R. Okay, we're just going to go with a D and an R here for domain and range. So stuff in the domain, right? We could have domain 1, domain 2, domain 3, just different values in here. And we ended up, right, this map to a certain range. Well, in the inverse, right, this range is now the domain. So this turns over into here, range 1, range 2, range 3. And this is now the domain. And these domain numbers, they're going to be over here in the range. That being said, it was easy for us in exponential functions to pick these values. It's going to be just as easy to pick these values for the logarithmic, but you have to remember they're in the range part, okay? And we're going to use that equivalent exponential form to help us figure out what's going on here, okay? So if we're going to go ahead and graph the function log base 5 of x, that is the equivalent. Well, let me finish off my statement. Okay, so equals y. The equivalent exponential form here, okay, is y raised, 5 raised to the y is equal to the x. All right. So that being said, hey, how about we pick the y's and then we'll figure out the x's because of it. All right. So here's my x's, here's my y's. Now notice I'm doing this first, okay? So I'm going to pick y is equal to 0, right? Y is equal to 0. If I put y is equal to 0, what's x have to be? X has to be 1, right? Because 5 to the 0 is going to be 1. So we're going to have 1. So what we're going to say here, right, is log base 5, right, of 1 is equal to 0. That's actually true for any logarithm with any base. The log of 1 for any base is going to be 0. Okay, because this is the same thing you're figuring out right here. Okay. What if we put in y is equal to 1? Right? So the equivalent exponential form here, y to the 1 is equal to my x. Oh, x must be 5. So what do I need to raise 5 to in order to get to 5? What exponent do I need on 5? It's 1. Okay, same thing. We're going to go ahead and work. What about y squared, right? So y equal to 2. What x is going to lead us to having, right, y equals 2, and that's going to be 25. And this is exactly how you solve these things, okay? So we're going to have log base 5, right, of 25 is equal to 2. 5 squared is equal to 25. All right, and I do apologize. I know that these are horrible. Okay, how about -1? Okay, so we're going to do 5 to the -1. What's that? That's 1/5 or 0.2. Okay, 0.2. I'm going to say it's 1/5. Okay, so log base 5 of 5 to the -1 is equal to -1. Okay, log base 5. Let's let right, y equals -2. Okay, so we have 5 raised to the -2. What is that? It's 1/25. So what I want to say is that, right, log of 5 to the -2, or 1/25, is equal to -2. So we need 1/25 here. I think that's 0.0625, I believe. So 0.0625, 1/25. Okay. So that's that's how you graph these things. Pick your y's first. You can even help and use this thing and figure out your x's based on your clever choice of a y. I won't tell if you don't tell, right? So every time we do like a square root, right, we always come up with, I'm going to do pick x to be 1, 4, 9, and 25. Right? How'd you pick those? Because they were easy square roots. So when I'm picking values for my y, my logarithms, we're going to pick values that are going to give us easy answers. Oops, this shouldn't be this. All right, that should be -2 here. Got a little bit ahead of myself. Now when I graph it, right, here's 1, here's 5, okay? So when x is equal to 1, y is equal to 0. When x is equal to 5, y is equal to 1. So we're out here at 25, right? We're finally going to crawl up to 2. Right? If I go to 1/5 here, right? When x is 1/5, then we're at -1. When we're at -1/25, let's look in here somewhere, right? We're going to go down here to real close. All right, so our graph is going to look something like that. All right, that's the other shape you have to know. Okay, so we had exponentials. We had horizontal asymptote, right? At y equals 0 with this. This is b to the x. Now we also have the inverse of it. So here we have, right, y equals log base b of x. Okay, this has a vertical asymptote of x equals 0. Okay, so there we go. That's pretty much what a logarithm is doing for us. Okay, and I'll repeat this from the last one. All right. It really is meant to make your life easier. Okay, I know from where it looks right now, it does not seem like this is making your life easy. Okay, but can you imagine being like a if you're an astrophysicist, right? When you guys study astronomy, and you've got lots of different spaces, right? And I've got to go 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, right? I mean, stars, the distances we talk about for stars are massive, okay? And I don't want to have to graph that on a linear scale where I get mad at my stats students for doing this because they do something like this. Right? I want to keep a consistent scale. And I want to keep things, in the middle here. But I can't do that with the massive distances and masses that stars have, right? I have to do logarithms. Actually, allow me one small rant. Okay. It pertains to logarithms, I promise. All right. When we have to watch the news, we're watching the news, and people are talking about the budget, and these people throw around million, billion, trillion. I mean, the human mind is not meant to like hold these numbers in your head, but I want to look at it this way, right? We want to say 1,000, right? 1,000 is a kilo, right? 1,000 grams, a kilogram. So okay, that's a meg, right? A million is a meg. So if you're looking at your computer files, you're like, oh, that one's only 3 meg. Like that used to be a whole hard drive when I was growing up. Okay, that was a lot. Okay, so these are the kinds of, we had like 100 or 360 kilobyte hard drive, if you can imagine. Then we get to like a 1 meg or a 2 meg hard drive. I never thought you could fill it up. Okay, but this is 1 times 10 to the 3, right? The log of 1,000, right? That's 3. So there's 3 zeros behind it. With the meg, right? It's 1 times 10 to the 6. The log of a million does a 6. Okay. So in your generation, right? Maybe when you were younger, right? You guys have gigabyte drives, right? So that's So you had a gig, right? And that was 1 times 10 to the 9th. Okay, so here we are. We're at 1,000. We're at million. We're at billion. Okay, so when people are talking about millions and billions, right, you should think, oh, it's got 6 zeros or it's got 9 zeros. Okay, billionaire, that's got 1 times 10 to the 9th dollars. Okay, the log of this thing, that's 9. I'll make that a 6 so you can see it. And then we get to trillion. Let me warn you that the English system, the British system, is a little different than ours. Okay, for a million, you got to go up to a million in order to go to a billion. Okay, so their trillion is really, or our trillion is their million, or billion rather. Since the American banking system is the one that is dominant, we get to use our number system. Okay, so what kind of hard drives do you guys have now? What kind of hard drives are you eyeing, right? You're looking at terabyte hard drive, okay? Which again, I'm gonna think I can never fill up. And you guys are saying that now. And then someday in the future, you're gonna be at 1 times 10 to the 18th. I don't know what prefix that is. But the log of this number here is just 12. Okay. So if you had to if it was your job to graph what budget expenditures were for the federal government, I wouldn't want to put thousands of dollars, millions of dollars, billions of dollars, and trillions of dollars all in the same graph unless I could shorten it and take the logarithm, right? I could do the logarithm of the budget, that'd be fine because the numbers are not so bad. But if they're going to say, okay, well, I want you to graph all this on a linear scale, how are you going to put thousands and then numbers that have 12 zeros after it on the same scale, right? That chart's going to be, it's going to take up like more than the whole room. So you don't want to do that. You want to convert. Okay. The other reason why I show you this is because nobody ever tells people hey, when you're thinking about this, right? There's 1,000, right? If you're a millionaire, you'd have to have $1,000 million to make to a billionaire. And to go from a billion to a trillion, you need 1,000 billions to go up to a trillion. Okay. So when you see people on the news and they throw around the millions, billions, and trillions, don't think about it that way. Try to think about it as how many zeros are behind that. Like, oh, there's 9 zeros, oh, there's 12 zeros. There's 1,000 of these in $1 trillion. Okay. So this drives me nuts because, we'll have a spending bill of $1 trillion. I'm like, okay, we've got a budget thing of $1 million. Like, there's a million millions inside of $1 trillion. And you're complaining about this. I mean, just think about how many zeros are different here. Okay. It'd be like a millionaire fretting over $1. Okay, that's what the difference between millions and trillions are, is $1 is to a million, $1 million is to $1 trillion. Okay, and most people don't even know their checking account to the last dollar. Some people do. You have to, but once you have once you have a slightly better job, you'll know it to the tens, you'll know it to the hundreds, right? You'll certainly know it to the hundreds. But I don't know my checking account down to the last dollar. It's not a concern for me. One time it was, but now I don't worry. Right, my checking account is here. I don't worry about the dollar amount because there's 3 zeros between them. So, just some ideas when you're listening to people talk about money. You want to seem like the smart person, right? Put it in scientific notation or think about it in scientific notation, and you'll have a much better grasp of what the magnitudes of these numbers are. And to keep you from getting swarmed because everybody's eyes glaze over. Nobody knows the difference between million, billion, and trillion. Okay, not as fast as they use those numbers on the news. So, okay. So we talked about the graphing. All right. Let's see. We wanted to look at equivalent exponential forms. Okay, Randolph. Okay, I don't want to go there just yet. I want to go to equivalent exponential forms. It's back up here, I think. Oh, come on, really? All right. Nope, I was wrong. This is like an important skill if you need to, you know, when you have stuff like this, okay, this is an important thing, is to be able to translate to equivalent exponential forms. Okay, so when I have like, what is log base 2 of 1/16? Now, I don't know off the top of my head. What I have to do is I have to say something like log base 2 of 1/16. I know that that's something, right? So 2 raised to what power is going to be 1/16? Well, I definitely need a negative in here, right? Because it's got to be a reciprocal. And then 2 to the 3, that's 8. Double it again, that's 16. So it's going to be 2 to the -4. So this answer here is going to be -4. And that's how you take these apart. Okay. Ln, right, natural log, e to the 6th equals what? Well, e raised to what power is equal to e to the 6th? This does not seem like a hard problem anymore, I hope, right? You're just going, oh, it's 6. Okay. Oh, these look, I hated these. I could not do, I hated these so much. Log base 1/2 of 1/32, right? Equals what? There's actually one nice thing about your book. Well, I mean, there's a lot of nice things about your book, but this is a really, truly nice thing about your book, is a lot of old math books would spend like an entire section doing this. Like, and I'll show you why that's a ridiculous thing to do in a minute. Okay. 1/2 raised to what is equal to 1/32, right? 2 raised to what power is 32? It's 2 to the 5th. Okay. So this one is just log 1/2, 1/32. This is to the 5th power. Okay, because I know 1/2 raised to the 5th, 1/32. Okay. Here, let's look at 45. That one looks hard. Right. Log base 3/2, right? Who would be crazy enough to do that? And then our equivalent form is 3/2 raised to what power is equal to 4/9. Oh, I think I need a reciprocal, so it's negative. And 3, if I square 3, oh, that'll take care of it. That'll be -2. Okay. So that's what we want to do with that. Okay. So with these, oh, okay, they just want to do 2 consecutive integers. Well, how many zeros would we, 40,000 would be what, 1, 2, 3, 4 zeros? And this is more than 40,000, so it'd be between 4 and 5. I think that's all they want us to do here. Okay. I wouldn't spend a lot of time on that. But there's 3 logarithms that we really care about and that we really deal with. Okay. It's log base 10, okay, which is LOG on your calculator. Okay. We have log base E, which is LN, it's not an I, on your calculator. Okay, so that LN button on your calculator, that's the natural log. And then we have an LG. So if you're going to go into computer engineering, okay, oops, oh, log base 2, we could do the same thing, right? Log base 2. You're not going to find this on a standard calculator, but if you're going into computer engineering, you might find a button or a function that says LG. It's log base 2, because computers count in 2s. Okay, so that's why we do that. Okay, so you'll notice you're like, wait, what about the button for log base 3/2? Like, there's no button for that. Nobody uses that. Well, the only time you're going to see it is in a math class like this one. So it's not the most important skill, but you know, it's one of those things. You want to get the A on your quiz. You're gonna know that too. Okay, but I don't spend a lot of time on this. So if you're like, I don't quite get this, I'm like, yeah, you're not losing that many points. You'll get it. Maybe not this time, but you'll get it next time. Okay. It's a terrible thing to say. You should get everything right. No. What did I want to look at? I want to look at properties of logarithms. That's what I want to look at. They have us look through this properties of logarithm things. Here we go. There we go. Properties, basic properties of logarithms. We're going to learn more properties. Okay. And there are formulas that you're going to remember because you have to remember them for the test. Okay. I get that. I can't think of formulas like anything like rotational momentum. That was one I like. Make sure you know it for the test. But I haven't had chemistry in over 35 years. And that is still seared into my brain for knowing chemistry. Okay. It's just one of those things where you're never going to escape it, right? I've had physics more recently, but you're never going to escape it. Properties of logarithms, same thing, okay? So log base b of 1. This one you can actually type in your calculator, right? Log of 1, right? Type this in, log 1 equals 0. Type in ln1 equals 0. Doesn't matter what the base is, it's always 0, right? Because b raised to the 0 power goes back to be 1. Log b, log base b of b, right? What do we have to raise b to in order to make it b? 1. Okay. So if we have log of b to some value here, okay, b raised to what power, right? B raised to what power is equal to b to the x. I tried to do a little bit of that when we were doing our graphs because I wanted you to kind of think, wait, is that what's going to work? Like, if you ask that question, yes, it is. So log base b of b raised to the x power is going to be x. Okay, great. And then this one is tricky. Okay, so remember how logarithms undo exponents? Well, exponents undo logarithms. So b raised to the log base b of x is equal to x. So if you take e raised to like the natural log of 4, what do you think you're going to get? It's 4. You could try that, okay? You try that with any number you want. I'm going to pick 4. Pick a different number. You're going to get the same thing. Well, you're going to get the same number you have here. So if we do second function e to the logarithm, pick your favorite number. So I'll try to fool you. I'll do 5. And what do you think we're going to get? We're going to get 5. You have to. Okay, that's a property. This one is tricky. People don't tend to remember this one. Okay, but this is how you get numbers out of a logarithm. Is you make the side the base. Okay. So there we go with that. Okay, that's a very important. It's a very important property. People forget it. It'll make your life harder if you forget. But those are your properties. Okay, and here's a much neater version of your properties. All right, in your book. So these are, I had a teacher, he would tell us, right, there's formulas you memorize for the test, and there's formulas you take to your grave. These kinds of properties, you're taking to your grave. Okay, you're going to remember these for the rest of your life, or at least until Alzheimer's takes them away from all of us. All right. So yeah, let's take a look at a couple of problems in here. All right. Oh, the domain. Okay, very good. Okay. So can we take the logarithm of 1? Yep. Can we take the logarithm of 0? Right, of whatever base. So what we're saying here is b raised to what power is equal to 0. And you won't find 1. Okay, no matter what negative number you put in here, right, whatever base you have, I mean, it might show up as 0 in your calculator, but that's only because of limits of the technology. No matter what I put in here, I'm always going to get something. It's going to be a fraction, but it's always going to be something. Okay, it's not going to be zero. It's going to be something bigger than zero. So log of zero, that doesn't work. And then if we try to graph it, right, we have a vertical asymptote. X equals 0 is my vertical asymptote. Here's the 0.10. Right? This is going to be asymptote. So log of 0, never going to work. What do you think about the logarithm of a negative number? They ain't going to work either. Okay, you can go to complex analysis and force the issue with eyes. Okay, which is really kind of cool. But as it is, we can't do the logarithm of a negative number. Okay, not in our class. So what has to happen here, right? If I have g of x log of 3 minus x, well, 3 minus x has to be a positive number. Okay. 3 minus x. Oh, I don't want greater than or equal to. I don't want it to be 0. That has to be greater than 0. Okay, 3 minus x has to be greater than 0. So let's see, how do we do this, right? Subtract 3 from both sides, and we get negative x is greater than negative 3. And then I'm going to multiply both sides by negative 1. Do you remember what we have to do this sign here? So we have to flip it because we multiplied or divided by a negative number. All right. So x has to be a number that's smaller than 3. If I put in 3, it ain't going to work. Put in 0, 3 minus 0 is fine. You take the log of 0, right? Or log of 3 rather. That's okay. What happens if I put x equals a negative number, right? We have x, we have 3 minus. What if I put in like a negative 10? It's a negative number, right? X is negative 10. What happens with the two negatives? This is really the log of 13. Okay, which we could do. All right. So be careful of those. Okay, that's the domain issues. Okay, so in this case, my domain would be, they want interval notation. So we went negative infinity up to 3. I wonder what the hardest problems are for this one. That one looks like the same problem. Oh. We could look at that one in a second. Okay, look at it now. Okay, so I have natural log, and again, the base doesn't make a bit of difference. X squared plus 17. Well, what's the graph of x squared plus 17 look like, right? Isn't that x squared with a vertical shift of 17? We'll call it 17. So this is my graph. Where is this negative? Never negative. So my domain here, all the real numbers, all positive and negative, right? Negative, negative, positive, infinity. Let's do a more interesting one. Let's do ln of x squared minus 16. Okay. This one, right? X squared minus 16. That's a drop. So we have to have a vertical shift. We're going to be down here somewhere. Where does it cross the axis? Right, make it equal. So we have x minus 4, x plus 4 is equal to 0, x equals 4, x equals negative 4. These are my x's, these are not my values. So I'm going through to graph this thing, right? Maybe it was harder. Negative 4, 4. Pick your favorite number. Okay, pick your favorite number that's smaller than negative 4. What's negative 5? Okay, I'm going to go ahead and say we have x minus 4 here. Okay, x minus 4, x plus 4. If I pick negative 5 here, we have negative times negative. We end up with a positive value. You can see that from the graph. Pick your favorite number between negative 4 and positive 4. It's 0, by the way. It's negative, positive. I multiply them together, you get negative. Pick your favorite number bigger than 4. So, okay, pi squared. Okay, pi squared minus 4 is positive. Pi squared plus 4 is still positive. my domain here, right? My domain is going to be negative infinity up to -4. I have to skip all of this stuff between -4 and +4. So union 4 off to positive infinity. We're just skipping the stuff in the middle. If we don't have a domain there, it's not going to work. Okay. So this is the kind of problem I actually do like to, this is the kind of problem I did like to do. Okay. Usually it involves some kind of weird factoring method like AC method. But this is the kind of problem I would ask. All right. What else are they asking here? Why are they just asking about domains here? Oh, because probably going to take a logarithm. All right, let's look at this one. I think this one's going to go somewhere interesting. So we have a function, and if x is equal to exponential, e to the x plus 6. Okay, and I know e is still intimidating for you. I understand that. But realize that when you get to calculus, e is going to be one of your better friends as far as numbers go. Okay. So what do they want to know? They want to do the domain. So what's their domain of this exponential function? Well, there's a shift of 6 here, so I have a new y equals 6 as an asymptote, and then we just have a function like that, right? Just drag my function and move it up by 6. Okay, let's see, can I do this? Book. Did I do something clever over here? Yeah, y equals e to the x. And then look what happens, plus 1. Oh, no. Let's say plus a. All right, we'll make a slider for a. We'll say it's 0 up to 7. It's like a step of 1. All right. So if I go ahead and change my a, what's happening to my function, right? It's just getting bigger and bigger and bigger. It's rising. That's all it's doing. Okay, it's making it kind of hard to see it. But there's 6. Looks a lot like just e to the x without anything, right? Except it's just risen up. It's just picked up and placed 6 points up on my graph. That's all there is. So when they ask me, like, what's my domain? Like, well, domain of any exponential function, right, is negative infinity to positive infinity. Oops. Are they really wanting me to check every time? They do. Write the range. Well, in this case, my range is 6. Because it doesn't quite get to 6, right? Off to infinity. Find the x-intercepts. There aren't any. Y-intercepts. Well, y-intercepts. So, here's what we have. Y-intercept is when x equals 0, what is y? So be careful about this one, okay? Because y is equal to e to the 0 plus 6. What is e to the 0 is 1. All right, so be careful about that. That's a place where students mess up, is they say, oh, it's a 0. It's automatically all 0. Like, no, there's a couple of functions that are not 0. Right? Do we need a point? I think we want a point. I think we want the 0, 7. All right. All right. We want y equals 6. I was hoping that they would make us figure out the inverse. I guess we're not there yet. And they're on a vertical asymptotes. So they're just making us review. It's probably just as well. I think when we go back and do our later in the chapter, we'll talk about inverses a little bit more because you'll have a little bit more tools to work with this stuff. Okay. So function is always increasing. Okay. We're doing this with paper and pencil, and we could just say everywhere, or this one. It never does. It's never decreasing. We would not have to worry about trying to do all of this. Hey, we just did this. Okay, we just did this. Notice when x was 0, we had y was equal to. These are all the wrong shapes. Oh, jeez. This is like a Facebook multiple choice quiz. I'm never going to do one like that. Okay, it's too easy. But again, I know it has an E in it, so I know it's scary. Okay. Tell you what. I just did that one. Yeah. We'll stop there. I'll let you guys get through some of that. If you have a question on one of these, like maybe one of the older ones, you're like, I can't remember that one. Please ask. We'll go ahead and do it. Okay. But that's our idea for logarithms. Okay, they're very powerful if you have to deal with a broad range of data. Okay, it's a very helpful tool, and it really helps think about really, really big numbers that are kind of far apart. So that's what you're supposed to be doing with it. All right. And next time we will go over, I think, more properties of logarithms. What are we doing? Where's my homework? Nope, I don't want that. I don't want the book either. I want this. This is what I want. Logarithmic functions, and then next week, or actually tomorrow, will be properties of logarithms. More properties. There's more stuff to remember. Again, this is not stuff you have to remember for like the test. This is permanent. Okay, like distance formula, Pythagorean theorem. You're never going to forget these. All right. So we'll talk about these. Okay. So we'll stop there. Okay, and we'll call it a day. All right. So thank you, everybody. I'm going to go ahead and stop recording.